Hey, Dr. Clark coming back at you with another Chapter 8 preview video. This time we're looking at multiple proportions. And in particular, we're doing the chi-squared goodness of fit test from Section 8.3. Let's take a look. So the goodness of fit test is similar to the other chi-squared test we've done before, but the key is that we're comparing data to a theoretical model. Instead of comparing proportions to each other, we have an idea of what should happen, and then we want to see if what is happening is what should happen. So for example, are these dice fair? Are people born evenly in every month? You know, if people were born evenly every month, you would have the same number of babies in January, February, March, April, May, etc. And we can test whether that's the case or not. Are used car sales evenly distributed through the month? Well, are at the beginning of the month are the same number as sold as at the end of the month? That kind of thing. All right. And all of these can be answered using a chi-squared test, but we got to do it a little bit different from how we did before. The question we're going to look at in particular is the fair dice question. And the way they tested this was kind of interesting. They set up some six-sided dice on a little ledge, and then they pushed them off the ledge, and they wanted to see if that was a fair way to roll the dice. Okay, and they put 5 on the ledge, the same orientation each time. So I think they always had the 6 up and the 3 out, and then they pushed them off to see, okay, if we always put them this certain way and then push them off, is a 2-inch ledge enough to make it fair? They repeated it 24 times, so they got 5 dice 24 times. That's 120 total rolls of the dice. And the question is, well, what would fair look like here? Well, if you got a 6-sided die, you should get a 1 1/6 of the time, and a 2 1/6 of the time, etc., which means you should get 21s, 22s, 23s, 24s, 25s, and 26s. That's what fair would look like if it was perfectly fair. Now, it's not going to be exactly 20. You're going to get some random chance. But if 6 kept getting rolled over and over, then it would pile up away from 20, and that would give us some evidence of a change. Okay? So how do you set up the hypotheses? Well, this is just like we've done before. Pi 1 equals pi 2 equals pi 3 equals pi 4 equals pi 5 equals pi 6 equals 1/6. We're saying that the proportion of 1s equals the proportion of 2s. They're all equal to 1/6. In other words, this method of rolling the dice is fair. Each face is equally likely to be rolled. And the alternative is that it's not fair. Not all the faces are equally likely to appear. So some of these pi's are going to be different from the other ones. Okay? And this pi sub I, that is the probability that the number I gets rolled. Okay? So if we're going to use symbols like this, we want to define what those symbols are. All right. What happened when they actually did the experiment? Well, it turned out they got a lot of 3s and a lot of 6s. So that's kind of making you think maybe it wasn't so fair because you got too many 6s and too many 3s. You should have gotten 20 of everything, right? That would be right about here. So you got too many 3s and too many 6s and too few of everything else. So that's at least, looking at the data with squinty eyes, you're kind of thinking, okay, yeah, it seems like there's something wrong here. But is it statistically significant? That's the next question. So we're going to compute the chi-squared statistic, and that's going to give us a sense of how strong our evidence is. And this is a slightly different formulation from the chi-squared that we saw last time. It's actually a little bit easier to understand it. Observed is what happened. Expected is what should have happened. When we subtract that, we see the difference from what should have happened from what did happen. We square it, and then we divide by what we expected to have happen. And we add those all up, and that's our chi-squared statistics. In our case, the expected is 20. We should have gotten 20 of each roll if the dice were in fact fair. So expected is 20 in every case. All right? Now, the observed is what ended up being rolled. So if we jump back here, that's the 19, 10, 31, 17, 15, 28. So what actually got rolled goes here. And then we just sort of do, okay, so 19 minus 20 is 1. 1 squared is 1. 1 over 20 is 1 over 20. 10 minus 20 is 10. 10 squared is 100. 100 over 20 is 5. Each of these gives you a different number. And when you add them all up, you get 16. Okay? So 16 is the chi-squared statistic. And you'll notice if all of these numbers were 20, 20 minus 20, 20 minus 20, 20 minus 20. You would get 0, and the chi-squared statistic would be 0. The further away those numbers get from 20, like this 10 minus 20, that's 10 away. That gives you 100. 100 divided by 20 is 5. That gives you a 5 right here. So the key to the statistic is when numbers are far away from what's expected, that contributes to a bigger chi-squared. So bigger chi-squared is going to be more evidence. Okay? In the applet, you can, in this case, select the data, but in general, you can just paste the data in, the value and the count, what the numbers are, how many there were, hit use table, and it'll make this little graph for you. It will also compute the counts and the proportions like so, and show you what that is, and then it will compute the chi-squared statistic for you. Now, we got 15.9 here. I think there's a little rounding. I think the applet uses these proportions, and it looks at the hypothesized values, and notice there's some rounding here. It should be 0.166666666. So there could be some rounding. That's why we're getting 15.9 instead of 16. But it's basically giving us the same thing. So it'll compute the chi-squared for you. We could do it by hand, but it can also do it for you. And then when we go to the simulation, we can simulate what would happen if we just did roll dice randomly, and it'll roll dice randomly, and it'll compute the chi-squared statistic in each case. And they're not always going to be 20, 20, 20 if you actually roll dice. So the simulation gives you the chi-squared statistics of what happens when you do it randomly. When you click the overlay button, it will overlay the theoretical chi-squared distribution. So again, this can be done as a simulation or a theory-based test. And then we just computed 15.969 or 16. When you click count, it'll tell you how often did we get something as extreme or more extreme as what we got in our sample. And it says the simulation gives us a p-value of 0.1. The theory-based is about the same, 0.007, pretty close to 0.1. And that's a small number. And when the p-value is small, that gives us strong evidence, in this case, very strong evidence, to conclude that these dice are not fair, or at least this method of rolling dice where you push them off the ledge isn't fair. Okay, so it's a similar way of making the conclusion. It's just the way we enter the data in is slightly different. We want to use the goodness of fit applet in this case. Okay, now there are validity conditions to the theory-based test. Basically, you need data from a single categorical variable sampled from the population, and then the expected counts have to be at least 5. That's key. So it's the expected cell counts that all have to be at least 5, not the observed, but the expected. Okay, in this case, the expected was 120 rolls, 1/6 each time, so we got 20 expected. So that was fine. We met the validity conditions. All right, and that's the main things we wanted to see in this section. So how do you set up a goodness of fit test? What are the hypotheses? What kinds of situations necessitate the goodness of fit? That's when you've got a theoretical model like, oh, the dice should roll 1/6 of the time each number, or a coin should flip heads half the time, that kind of thing, where you've got a model and then you've got data and you want to compare the data to the model. We talked about computing the chi-squared statistic. We learned how to make the applet do it for us, how to have the applet compute p-values for us, and then those validity conditions needing 5 in the expected in each box. All right? So I look forward to seeing you in class. This is just the overview. We'll get all the nice details in class, and we'll see you then.